Morning, good afternoon, and good evening, everyone. So, in our previous video, we talked about how we can use double integrals in polar coordinates. So, instead of using our typical x and y, we're doing something with r, which is our radius, as well as our theta, which is our angle, right? So, we translated those xy values to something like r and theta. This helps us analyze motion rather than just the position of xy given we're in some 2D plane, right? Okay, now let's move on to actually talking about the double integrals because in the previous video, more or less, we just tried to do a brief review of what exactly are polar coordinates since I haven't actually done it before. What exactly are polar coordinates? How can we use them instead of XY? What makes them useful in some way? And we've noticed that they are pretty useful when evaluating double integrals, especially when our region is kind of circular. So not necessarily something like a square or something else entirely, right? So it's just another technique for us to work with double integrals at the end of the day. Okay, so let's get started, right? So now we talk about double integrals here. So double integrals in polar coordinates. Oh, okay. So the regions in figure 2 are special cases of a polar rectangle. So this was figure 2. Wait, where was figure 2? What in the world? Oh, apparently we call this a polar rectangle. Both of these things are polar rectangles. Now I need an explanation on why. Oh, it's because of these. So remember when we were talking about rectangles when we did an X and Y? We had certain limits of X and Y, but here instead of X and Y, we're doing R and theta. And so if we translate that back to XY, it becomes circular. So these are what we call, this R, we call that a polar rectangle. So that's interesting. And so in the next figure, which I'm going to show, where in the world is my screenshot? Okay. So in the next figure, I'm going to show something a bit interesting. Okay. Taking a while for the screenshot. Oh, too big. There we go. So what's up with these figures? What are these? In order to compute some double integral, so actually R is the region. This particular region, the green region, this thing, that one. So R is what we call, so that capital R, that we call that a polar rectangle. And we somehow divide the interval AB into m subintervals, R sub I minus 1 to R sub I of equal with delta R, which is equal to B minus A over M. And we divide the interval alpha beta into n subintervals theta sub j minus 1 to theta sub j of equal with delta theta. Then the circles r equals r sub I and raise theta equals theta sub j, divide the polar rectangle into the small polar rectangles r sub ij, which is shown in figure 4. So what in the world did I just say there? We're doing another double Riemann sum. But this time, instead of xy, we're doing it for r theta. That's pretty much all I said, right? I'm not going to get into the double Riemann sum technicality anymore because we've done it in a previous video. Wait, do I have a Riemann sum exercise? If I do have a Riemann sum exercise, then I will do it. If I don't, I won't do it. Okay, I don't have it. So I'm not going to do a Riemann sum exercise. Cool, cool. Yeah, we're going to be analytic here. We're not going to do some approximations, so I don't need to know the Riemann sum behind it. But it's pretty cool though, knowing the Riemann sum. I'll write the notation a bit actually. So this is the notation of the Riemann sum of figure 4, how we can divide that thing. So it's again a double Riemann sum. I think this was I, then some N, some J, then F, and then some R sub I, some sample of R, and then some sample of theta, and then R sub I, and then some sample again of theta, but this time with sine. So it's that two variable function there with some change in my area sub I. So it depends on the area, right? Because these have varying areas. So now we even include this delta A sub I. And apparently this is the same, or yeah, so here we can say that this change in my area sub I is actually just R sub I. Oops, what my okay. My R sub I sample, and then my change in my R, and then my change in my alpha. So that's just equal to that. We can just replug this in here, but it doesn't really matter. But that's the idea of a double Riemann sum, right? Mm-hmm. You could even rewrite it as some other function. Oh, is that the... Oh no, I'm gonna go straight into the integral because I don't want to... I want to keep it simple. So for the integral, it's basically the change to polar coordinates. Right? In some double integral. Now, what do I mean by this? What I mean is, okay, we'll write a brief background here. So let's say f is some continuous function. It's on a polar rectangle. Let's say that's R. And this is, that R is basically this thing. Oh, 0 less than or equal to A, less than or equal to R, less than or equal to B. So we're saying here that A and B, or A is positive, or 0, right? They also have some alpha, which is in between my theta, in between some beta. These are just angles at the end of the day. And then we also say, what is this? So let's say f is continuous. And then we say that the difference of this beta and alpha is this thing. So beta minus alpha, by the right R, I meant 2 pi. So it should be within that revolution, the difference of these two, right? Then, so here's the integral. I'm gonna just hop right into it and then just maybe do a bit of an example here. This thing. This is equal to alpha, beta. This is equal to AB. And this is some function f, which has r cosine, r sine. And then r dr d theta. Okay, and so the formula so this thing, it says that we convert from rectangular to polar coordinates in a double integral when we say that our x and y are r cosine and r sine. And we use the appropriate limits of integration for r and theta, right? So for r, we said it's between a and b. So here we integrate with respect to r first, and then we integrate with respect to theta. But we can reverse the order. And then we replace our dA by r dr d theta. So there's an additional r factor there, right? And so the classical method for remembering this is going to be shown in some figure. Okay, let me just show the figure. So here's a way to remember that thing. So if we look at the picture, or at least the picture I'm gonna show here. There, if we look at that picture, how does that help us remember? The infinitesimal, or the smallest polar rectangle, can be thought of as an ordinary rectangle. So let's say that again. The smallest polar rectangle can be thought of as an ordinary rectangle, right? So if we make our polar rectangle really, really, really small, it's gonna look like an ordinary rectangle, and it has certain dimensions, which are r, d theta, and dr. And so that change in area, or that small change in area, is r dr d theta. So that's the idea. Mhm. Here, if we look at this green thing. So this looks like an ordinary rectangle in a way. So just to kind of make it nice, this one's r d theta. That side, this one's dr. So to get the area, or the area of this is dA, it's just basically this times this, right? Okay, so let me go ahead and do an example here, and I'm going to go ahead and jump to some examples from the homework. So the first example tells us that we have to evaluate this integral, 3x to the fourth plus 4y squared, where R is the region in the upper half plane bounded by circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So where R is above, R is in the upper half plane. What do I mean? We have a plane, the upper half. That's what I mean. And then it's bounded by these two things. So a unit circle, as well as a circle with radius 2. So that should be 4. So how do we solve such a problem? Well, if we go back to our typical idea, find the integral, solve. As simple as that. So here maybe I'll translate my r into a set here. So for every xy point, so here we're not even using anything from polar yet. Here we're saying that 1 and 4 are the bounds of this circle equation, right? So we know that. And apparently this is what we call a half ring. And so let's translate it to polar coordinates. So how do we do that? Here we see that r, or okay, let me write it in a very step-by-step way. So here we have x squared plus y squared equals r squared, right? And so that means 1 is less than r squared is less than 4. And so that means 1 is less than or equal to r less than or equal to 2. That's the first bounds. Now, how do I find my theta? Because I also need that stuff. Well, to find my theta, that's the first idea. That's my r, right? Now, to find my theta, I need to say this is equal to r cosine, and then this is equal to r sine. So when I square them, that's that. Now, how do I find my r cosine and r sine? Or specifically, how do I find my theta? Algebraically, let's see if it's possible. You know, this thing. Mhm. Mm. Okay, I don't think we can. We can use algebra to find this. Because I mean, we're in the upper half plane, so we have to get clues from something like what's our domain or what's the area that's covered. So here, I think it would just be from intuition. So from intuition, we're going to say this is 0 to pi, right? Why 0 to pi? Because we're rotating in the half, the upper half. And it also says it's a half ring. And so from there, let's actually get the integral. Like we're going to solve the integral. So what's the integral going to be? Well, we just copy what we looked at before. So that's my theta. My dr is 1 to 2. Then I have my function, but then my function will be translated to something else. So this is 3, pretty sure this is r squared, right? 3x cosine squared. So r squared cosine squared plus I think it was 4y squared. So 4, then r squared again, then y squared. So 4y squared. And then dr, or whoops, r dr d theta. So that's the whole integral, this thing. Now, of course, I solve it by plugging in everything, obviously. So here I'm just going to solve the first one. So you can say 1 to 2. This is 3r cubed, so I'll treat it like normal. 4r cubed, right? Oh, wait a minute. Whoops. This is 3x. Oh. So that's why I was wrong the whole time. That one's 3x, so this means this is just r. And none of that other stuff. So this is, I think, just theta here. Right? Then this is r squared sine squared. So this is r squared, question mark. And this one's nothing. There we go. Nice and easy. Now we have dr, right? Now I multiplied all of the r's. Now with respect to r, what is this going to give me? So here I could factor out an r. Or actually, I think we just integrate here. Yeah, I feel like integrating might be our best course of action. So here I leave 3. This is r squared cosine theta. So 3 cosine theta is just there, right? R squared is r cubed over 3. So it's actually r cubed cosine theta. And then this is plus. And then this is r to the 4th over 4. So this is r fourth. And then sine squared. Yeah. And then we basically get a number out of it. So it's kind of like just the same with the previous one, 1 and 2. Here I plug in the 2, so I get 8 cosine theta. Wait, do I plug it in the... Oh yeah, I plug it in here. Then 8 to the 4th is something. Oh my goodness. 4096. Whoops, did I mess something up? R cube, r to the 4th sine squared. Okay, somehow he managed to simplify everything, but okay. 4096 sine squared theta. So that thing, I'm going to subtract it to 1. So cosine theta plus sine squared theta. So what happens here is I take this out, minus, minus. So this is 7. This one is 4096. Wait a minute. 2 to the power of 4. What did I do? This is 16. Anyway, I think I'm tired. Okay, so we get that. Here we go. And then we get 7 cosine plus 14, 15 minus, I think. Oh no, what do I do now? Put 16 and then 15. Whoops. Yeah, this was 16, and then now this is 15. And then now we integrate that thing, right? So now we integrate from here to here of this thing. And we're going to treat this like a normal integral. Now we have d theta here. So this is going to give me, uh-oh. I mean, So 7 cosine is just 7 sine. That's not an issue. But now my issue is this thing, 15 sine squared. How do I integrate sine squared? Well, it's a half angle identity. So I think this is just a half. I forgot how it works. I think it was like a 2 over something something. Yeah, I totally forgot how it works. Integrals. Let me see. There was something about integrals too. Something I'll also put in my cheat sheet. Okay. So here we have okay. Yes. So here oh my God, where was it? Integral. Mm-hmm. Ah, there we go. So just a note for me, and in case I get something like this again, it's a half angle identity. So what I'm saying is this becomes something like this. 15, and then here we have 1/2 of 1 minus cosine 2x. Right? It's that simple. No, it's not simple, but kind of like that. And we have d theta here. So again, it's just a trig identity thing. Oh, this is theta. Oh yeah, 0 to the sine of x here. Okay, so here, yes, I have that. Okay, let's probably evaluate it a lot nicer. I want it to be clean. This is 15/2 of this thing. And going from the back, this 15/2 minus this thing. There we go. Okay. And then from there, I'll probably just separate it because there's just too much going on. Then I subtract this thing. But these are pretty simple integrals to do, right? So here I just get 7 sine. 7 sine theta. Or actually, I could just bring this out and then get something like this. This one, I could bring this out and just add the pi. Then this one, I could bring this out. This is a half of sine. Then I could take this one out. So this becomes like that. I'm just making my life easier at this point. This becomes 4. Then this becomes pi. And then from there, okay, well, I get 7 times sine pi. Sine pi is just 0, right? And then sine of 0 is just 0. So this whole thing is 0. So I have 15 pi half. And then this is minus 15/4 of something. So 2 pi is 0, I think. 0 minus 0. So again, I get 0 here. So these are both 0. So I'm left with this number here, which I think might be my answer. Yes, that's the answer. Cool. Okay, now let's do exercises on these topics. And I have a couple of them actually. How many items are these? I have like 10 of them ish. Okay, I'll do like 4 or 3, 3 to 4, and then I'll do the others later. Okay, let me go to the homework and do some stuff. So here, oh, it's 11 to 21. How many is that? So you get their difference, that's 10 plus those two, so that's 12. Or 11, I think. 12, no, 10, no, that's 11. Yeah, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Yeah, it's 11. Okay, it's not 10, so it's 11. So here, let's evaluate integral with polar coordinates. So we're going to use polar coordinates to solve this problem. So how do we do that? Let's say we have this. This is a D, by the way. So we have that. And we're going to say the D is the top half of the disk. So we say it's the upper semicircle. So the center is actually an origin here. And the radius is 5. So what does that mean, right? So here, the first thing we want to do, so if we do a step-by-step, is find bounds. But we're going to do it in terms of polar. So my bounds here are going to be something with R and something with theta. So it's a polar rectangle in this case, right? So my x squared is the same as R squared cosine squared theta, right? And so what's my R? My R is from 0 to 5, right? The clue is actually here already. Center as origin, radius is 5. So we can say that this is that. And then for my theta, so my theta is from where to where? The top half. So when we see something like a top half of a disk, we know my theta goes from 0 to pi. It's really as simple as that. No need to complicate these two things. So when we say something like top half of disk, then we immediately know that's this thing. And when we see something like center as origin, and a radius of 5, well, we immediately think of this thing. And so my region, if we want to make it really fancy, is just a set of all of these, r and theta, such that we have these things. Okay, I'm just gonna do this for once, I'm not gonna do it later. Next, we find integral and solve. It's really all about this idea of finding the integral. So the first step is to check if the integral is correct. Then the next step is to try and solve it and see if you don't mess up. Because I do mess this up a lot. So here we're gonna integrate first with respect to r, and then with respect to theta. So for my theta, I put here 0 pi. For my r, I put here 0, 5. Then I put my function x squared. And then instead of dA, I put r, dr, d theta. And then I solve. So how do I solve this thing? Well, first let's start off with this. R dr. Here I could immediately take out the x squared. So I'm left with x squared r, or r, I think it was this. Get the antiderivative. Here I get 5 squared, 25 over 2. So I get 25 over 2 x squared. And then from there, I integrate that thing. Oh, wait a minute. Oh, shoot. I forgot to translate this. to Yeah, so I needed that other thing. Whoops, my bad. My bad. Whoops. I just realized. Okay, so once we get that, we need to also have our function in terms of r and theta. So function should be in r and theta. Or r, or just theta, it doesn't matter. Because we're using polar coordinates technique. So x squared in this case is r squared cosine squared theta. And so this is going to be r squared cosine squared theta. R dr d theta. And then we start solving it. There we go. So now we say, okay, this is r cubed. I could leave this thing out. Here I get, so I leave this whole thing out. This is r to the 4th over 4, 0 to the 5th. And then here I get 5 to the power of 4, 625 over 4. Is that possible? Oh, no, it's not. Then this is cosine squared theta. See if I got that one. Probably did-ish. Okay, now let's try 0 to pi here, where I derive this whole thing, d theta. So I could take this thing out. Oh, I could use that half angle identity, right? So there's gonna be, let's not take it out first. 625 over 4. I think this was a half of 1. And instead of minus, if I remembered correctly, I think it was a plus. Yeah, instead of minus, there's gonna be a plus. So plus cosine 2 theta. Right, that's the whole idea there. And then we can start simplifying these things. So I'm actually just gonna take both of these out because why bother, you know? So this is 625 over 8. And then this is 1 plus this thing. So we basically just took out that part because we don't want to make it complicated. So here when I integrate, this one's some constant. So yeah, this is just pi. I think I can add this one here. How do I know it's pi? It's 1 pi minus 0. So it's pi. And then this one is cosine 2 theta. This is a half sine of 2 theta. If I take the derivative of that, I would get this. Then I evaluate that from 0 to pi. So here I would get, I think this was 2 pi is 0. That's just nothing. And then you make this 0 anyway, so it doesn't really. This pi plus 0 minus pi plus 0. Wait a minute, is that it? No, no way. Yeah. Uh-oh. Wait, so everything's 0? That's not right. Oops. Yeah, if this was pi plus 0 minus pi plus 0, then this one's 0. If I multiply that by 0, I get 0. So that there's something wrong. Or, I don't know, this might be right. Again, not super confident here, but we'll see. Radius. Okay, so I did get the bounds, which is good. And I did get the integral. Yeah, you already put r cubed here. Oh, I forgot something. I forgot sine. What? Why sine? X and y? Oh shoot, was there a y here? Wait a minute. Oh my goodness, there was a y. That's why. I totally forgot about the. Okay. So the problem I was solving was kind of wrong from the beginning. There was a y there. So I needed to also do that. This is y. I think this was r sine. Whoops, my bad. And so from there I have r cosine squared theta r dr. I also have r sine theta. And then r dr d theta. There we go. Now that's so all of this is just wrong, pretty much. Oh my goodness, what am I doing? I meant to like erase the thing. Yeah, so you see that's what you get for math. If you get one of them wrong, you solve for some of them, you get everything wrong. Okay, let me integrate the first thing first. So here, r squared r to the fourth, right? And this is some value here. And this is dr. So I immediately take out my cosine squared theta sine squared. So I'm gonna get this thing. Then I integrate this to the fifth. And then what do I get? Is there a nice trig thing here? Cosine squared. I was thinking of something nice for a trig, but I guess I'm not that. I don't have a solid foundation for trig. I'm not gonna bother. So this is 3, 1, 2, 5. Divided by 5. 6, 2, 5. 625. There we go. Now I solved that whole thing using a. Oh, and here's the tricky part because I know I'm gonna integrate with respect to theta. Oh shoot, is this biparts or is there another way? Well, if I do, okay, let me try to modify this a little bit. This is a half. Then I think this was cosine squared. No, this has to be sine squared for it to be 1. So that doesn't make sense. If I do a half angle here, cosine 2 theta, and then do a sine theta. I'm trying to think of a nice way to simplify this. So this is a half. Or I think I made this one worse. Yeah, this is a half plus and a half. Oh, but then I get everything half. If I do this. Yeah, and I get everything half here. There's also sine. Oh, shoot. Oh, that just got even worse. So let me not do a half angle identity. Well, if instead I take out one cosine here. Let me do cosine, cosine, sine. And then we did have a trig for that. So this is cosine, and then this one was a half of this thing. Okay, this one's a bit better. Actually, no, I'm not super sure. What's the best way to go about a problem like this again? Because I totally forgot. Is it biparts? Oh shoot, it's just a U sub. Okay, no way they're making me do complicated integrals again. This is this is hell. Cool. Okay, so we have that. Okay, nothing to worry about. Now I do 0 pi here. So immediately I just do this. I take out my 625 because I don't want to worry about it anymore. And I have this thing. And then this is going to give me, so 625. Oh, this is a U sub. This is a U sub. I say my U is, what the hell is my U? Take the derivative. Actually, I think it could be any. Okay, I'll just make my U my cosine squared. What did the AI say? So the AI said he made U cosine theta. Yeah, he made the U cosine theta. Let's try this. I don't know. I'm feeling a little bit. So here I do a chain rule. Or I do this and then a chain rule. Oh shoot, I made it worse. Because even if I have this as my U, I'm gonna do a D. Uh-oh. D theta, and then this one's over here, and then D is. So I can't really cancel it out. So I need this to be a U. Cosine theta, not cosine squared theta. Because I can cancel out everything. So my derivative or du is going to be, no, negative sine. So nice and simple. This is d theta. And so my d theta is going to be du over this thing. And so from there I get 60. Oops, I forgot bounds. When my theta is 0, my u is cosine 0, which is 1. When my theta is pi, my u is cosine pi, which is negative 1. See if I got that one. Yes, this makes sense because then I put the negative behind and we're good. So how would this look like? So this is 625, 1, negative 1, and then this one is u squared sine theta. D theta is du over negative sine theta. Look how nice that is. I can cancel that, right? And from there I get 625, 1, negative 1. Or in this case, I do a negative here. So this switches it to negative 1 and 1, right? Oh wait, if it switches that, then this one is now just gone pretty much. That was the purpose of it. Yeah, and then now you have u squared du, which is a nice integral if we think about it. Yeah, it's a nice integral. So yeah, yeah, I got the right answer. So 625 u cubed over 3 negative 1 to 1. It's just gonna give me like 1/3 minus negative 1 2/3, and then that's just 1 to 5 0 over 3. And that's my final answer. So that took a while with doing integrals like that. But yeah, that's the idea. You want to get into the habit of solving long integrals. God, it's been like a 125 thing again. I feel like Calculus 2 is way harder than Calculus 3. Calculus 1 was definitely the easiest. Or I think I just studied too much that time. That's why it's the easiest. Okay, let me do number 12. So again, we evaluate integral. So that same pattern. But instead of it being, okay, actually I'm gonna do this and then call it a day for now. Okay, so again, with the evaluating integral with polars, here we get this thing, the e to the negative x squared. And I think this was minus y squared. Then this was dA. And then from there, D is the region. So D is a region bounded by, so D is bounded by a semicircle. So here we are again with the semicircle X. This X is equal to square root 49 minus y squared. And the y-axis. So it's actually a semicircle and then a y-axis. So it's a quarter circle. If we think about it, it's a quarter circle, right? Those are the bounds. Let me see if this is similar. Yes. So first things first is we want to find the bounds. How do I find bounds here? This one's tricky. So it's bounded by some semicircle of this. Then we have a y-axis as well. So if we draw what that is, I think it's more on the drawing side. If we draw this thing, ooh, this here is the same as x squared. Oh, I think I get it. This is x squared plus y squared equals 49. And so that means this is originally a circle with radius 7. So some 7 here. And then we're saying it's bounded by a y-axis. It's an upper semicircle. So an upper semicircle like this, right? This is 7. And then it's bounded by a y-axis. So it's bounded by this thing. Now, which side? I don't know. I would just go for this part. So I think region, the region that we're talking about is this thing. But yeah, this whole thing is x is equal to square root of 49 minus y squared. This one is y equals 0. Or true, x equals 0, my bad. Because y-axis is when x is 0. Okay. I should have just said y-axis. I don't know. I don't know what I'm doing. I should have just said y-axis. That's the y-axis. It's bounded by that and then this semicircle. So the region is obviously here. Yeah. So what does that look like? So that looks like my R looks still from 0 to 7. But then my theta looks a bit different. My theta, as I'm rotating here, I can't quite see my drawing. Oh, shoot. I can't see it. As I'm rotating. It looks like it only goes from by half, right? It doesn't go beyond that. And so that's for all of my R and theta values. 0 to 7, 0 to pi half. So those are the bounds, right? I think. If I'm wrong, please correct me. But these are what I think the bounds are. So it really helps to draw what these are. So it's some semicircle here, some y-axis here, and then this is my region D. I don't know why I did that. I should have just done like a different color at least. That was my region D. Okay, so now what's the next thing? We need to find a function which should have an r and a theta. And we're going to base that off the original. If you want to use polar coordinates in this case. Oh, so that one's a natural exponent, so an exponential function. Right. How do we do that? Well, actually, if we look here, my x should still be the same thing, right? So my x is still the same thing. R cosine. By definition, these are the same for every value. So we're just gonna have to deal with it. Yes. And so from there, you can just pretty much like just plug it in and then see what happens, right? These are going to be all the same thing. So we have e to this thing, right? I think that was my function. Oops. Yes, that's my function there. Now I just plug it in. E to the negative r squared cosine squared minus r squared sine squared. Done. That's it. That's the idea. And then from there, we just solve it, right? So how would I solve such a thing? My DA is also that. So now I find the integral and solve. So here I get something like my outer, which is my theta values. So it's from 0 to pi half. Then my other one, which was from, I think, 0 to 7, right? Because that's my radius, 0 to 7. And then my function in terms of r and theta. D theta, whoops, r, dr, d theta. Now, here's the tricky part. How do I integrate this whole thing? It's tricky. Okay, let me try to factor it out. Let me see. R squared cosine. Oh, I think I could do something with this. Yeah. Let me see. Try to think. Okay, this one is gonna it's like part of the computing thing. This thing. What else can I say? I could factor out an R squared, right? So I factor this thing out, I factor this thing out. And I'm left with this thing. I think this might be easier than I think it is. Well, that cosine squared plus sine squared is 1. And so that means it's just -1 r squared times 1, which is -r squared. And so that whole thing was just -r squared. It was just like a simplified expression. Because by definition, that was true, right? Cosine squared and sine squared, this thing is always going to be equal to 1, no matter what. So that was the idea there. And then here's just -r squared. So let's evaluate that easy integral. Okay, I'm kidding. It's not, it shouldn't be that easy. E to the, so this thing is -r squared. I think there was another r here somewhere. Yeah, there's an r here and a dr. Great. So how do we do this? Well, at the top of my head, I'm thinking of a u sub. Right, so I'm thinking of a u sub. Let's just do the u sub. So here I have my u, which is, do I do a negative or do I do a positive? That's the other thing. I don't want to do a negative because that would affect the bounds. So I'm just going to do r squared. It's also this thing of picking what the right u is, which to me, I still find it hard because there's no exact way of doing it. So it's really, for me, it's just trial and error. Okay, so I have dr is du over 2r. Okay, this makes sense. And then when my r is 0, my u is 0. When my r is 7, well, u is 49 because I squared that thing. U is equal to r squared. And so I get something along the lines of this. 0 to 49, e to the negative u, r, and then du over 2r. Here I get to cancel out the r's. And so I get 1/2 outside, 0 to 49, e to the negative u, du. And then if I integrate this thing, I'm going to get 1/2 negative e to the negative u. Right? How do I know? If I take the derivative of this thing, it's going to cancel out the negative signs. So this is good. Right? And then from there, I just plug in the values I need. So this one is negative e to the minus 49, or e to the negative 49, minus negative e to the 0. Yeah, so it's just, or actually I could have just taken out the negative part, like plop it here maybe. And this would have been easier. This one is just e to the 49 plus 1, right? Actually, it's -1. My bad. Yeah, because this is negative. I get e to the 0. There we go. Yeah, that's that thing. Cool. And then from there, now what do I do? Did I get it? Oh, no, I need to do the theta. Oh, but then for the theta, it's not really an issue anymore. Or at least I think it isn't. So I have to integrate this whole thing. Here I just, well, this thing times pi, that's it. So it's really just negative pi of this thing. I don't know how you want to put it, but that's how I'm going to put it. And that's it. Hopefully, I think that should be that. Yeah, the trouble here is the first part, especially the simplifying one. I feel like that one's that one's something else. Let's see if I set it up correctly though. Oh shoot, maybe not. I did from 0 to pi. Oh, what the hell? Why did pi half? That one's pi half, or I don't know, pi half. Oh, and then this would have been a different answer because I would multiply the pi half here, so this is pi fourth. I almost forgot about that. Here, on the other hand, wait a minute. Did I draw this thing wrong? From 0 to pi half. What? Uh-oh. Oh, because it's from x. Whoops. My bad. Yeah, so this was from, no, not here. This one's y equals square root of 49. Y. Yeah, so this one is supposed to be from the y-axis. Yeah, so it was supposed to be from here to here. So we need to include this thing as well. So yeah, it's from negative pi half. Right, yeah. So that was the yeah, that was the difference. That was what we need to include. Cool. So this was supposed to, yeah, it was just a trig error on my end. So nothing, I don't think anything's wrong with this one. Right, so I need to include this. Hmm. Yeah, so there's still some integrating to do here. We'll see if I'll double check before I start solving more. Yes, so the first one is, oh, cool. So we did get the first one. Yeah, negative one. Yes, we did get it. Outer integral. Okay, it's a pi half. Funny enough, we did get the right answer. Oh yeah, another tip. Since we're solving for more, maybe we'll just do this. Just to make it nice to the eye that, okay, we're gonna be integrating more. So let's prepare. Let's not do any negative stuff outside. That's gonna ruin the computation. And so how that's gonna look like is now, actually I don't even need to. I just realized because this is a constant at the end of the day, so I just need to do something like this. And then it's gonna be pi half minus negative pi half. And then that's gonna be what? 2 pi over 2. And so that's gonna be pi half 1 minus e to the negative 49 power. And that's the answer. Write that out. So it's pi half 1 minus e to the negative 49. And we're done. I think. We'll see. But I think the hardest part was the simplifying one because that would have made our lives very, very easy. And we did it. Nice. Okay, I'm gonna do the remaining ones after I eat because it's lunchtime here. I'm hungry. But yeah, I hope you guys enjoyed and learned a lot, and I'll see you all in the next video.